Hello, today we're going to do another interesting calculation. We're going to calculate the infinite sum of n squared over n factorial. So this is by no means an easy sum, but I hope you'll be able to follow along. And before we do anything, we're actually going to prove a fact. You might know this fact already, but we're going to prove the Taylor series for e to the power of x. Now, the general formula for a Taylor series is f of x, so that's an arbitrary function, equals the sum from n equals 0 to n equals infinity, or approaches infinity, of the nth derivative of f evaluated at 0. Now, the f in the exponent there, so that means the nth derivative of f. So that's important to keep in mind. And then over n factorial times x to the power of n. So this is a general formula that can be used on any function. Of course, not all Taylor series converge everywhere, but the one for e to the power of x conveniently does. So we're going to use this one. So the first step in calculating this Taylor series is going to be calculating the nth derivative of e to the x. So we're going to take the derivative of e to the x once to see if we can figure out any pattern. And as you might know, the derivative of e to the power of x is equal to e to the power of x. So actually, this is a really easy example of a Taylor series. Because the first derivative of the function is itself, it's always going to be itself. So f to the power of, the nth derivative of f is always going to be e to the power of x. That means that the nth derivative of f evaluated at 0 is always going to be e to the power of 0. So that's always going to be 1. So actually in our case we can immediately just disregard that part of our function, and we can just write down that e to the power of x is going to be the sum from n equals 0 to infinity of x to the power of n over n factorial. So obviously that looks pretty complicated, but we'll write out some terms to make a little bit more clear what's going on here. So we've proven the Taylor series for e to the power of x. Now actually we're not really going to use the longer written out versions of this Taylor series, so we're just only going to use this summation notation. So let's bring that up to the top. So we now have e to the power of x is equal to the sum from n equals 0 up to infinity of x to the power of n over n factorial. Now what we're going to do in this case is we're going to take the derivative of both sides. And you'll be able to see soon why we're going to do that. So let's get right into it. So we take the derivative. So we got the derivative of e to the x is equal to the derivative of the sum from n equals 0 up to infinity of x to the power of n divided by n factorial. Now, as we just discovered, the derivative of e to the x is just going to equal e to the x. And then the derivative of that summation, well, we're actually just going to have the derivative inside of our summation. So we need to take the derivative of x to the power of n with respect to x. So what's that going to be? Well, we need to use the power rule, and that's going to be n times x to the power of n minus 1 all over n factorial. Notice that n actually doesn't get affected here, or the n factorial, that's just a constant. We're only differentiating over x. The next step we're going to do is we're going to multiply this equation by x. So now we get x times e to the x is equal to, and then the sum from n equals 0 up to infinity of n times and then x to the power of n minus 1 times x all over n factorial. Now notice that, of course, we can cancel out that n to the power of n minus 1 times x and just write n times x to the power of n. The next step we're going to do is we're going to take the derivative of this equation as well. The first derivative of e to the power of x times x, we need to use the product rule. So that means we have to first differentiate the first part of the function and then the second part and add them together. So that's going to be the derivative of e to the x is just e to the x, so that's going to be x times e to the x plus, and then the derivative of x is going to be 1, so equal x times e to the x plus e to the x. And then that's going to equal, well, again, just like last time, we can just take the derivative inside our summation. So we're going to get n squared times x to the power of n minus 1 all over n factorial. Now we've got this function, which we could call just f of x, which is going to be x times e to the x plus e to the x, and also, of course, equal to the infinite sum from n equals 0 up to infinity of n squared times x to the x minus first power all over n factorial. So we've got these two expressions for the same function. Now what are we going to do? We're actually going to plug in x equals 1. So what is f of 1 going to equal? That's going to be 1 times e to the power of 1 plus e to the power of 1. Let's just write it down immediately. That's obviously going to be 2 times e. And then on the right-hand side of our equation, we're still going to get our sum from n equals 0 up to infinity, and then n to the power of 2, and then times 1 to the power of n minus 1 all over n factorial. Now notice that 1 to any power is just going to be equal to 1. Now we can rewrite this as the sum from n equals 0 up to infinity of n squared over n factorial. And that, believe it or not, is our answer. So we've used this Taylor series for e to the x, we've differentiated it and times it by x, differentiated again, and then we actually magically got our expression that we needed. And also we got our expression in a simple function, which allowed us to just plug in a value, 1, which simplified it and got us our answer of 2 to the power of e, 2 times e, of course. So I'll rewrite it quickly so we got a clean final answer. Hope you liked this video. It looked complicated at first, but actually we got a pretty simple and elegant technique to solve this. Thank you so much for watching. If you have any tips for me, let me know. Also, if you like the black colors, let me know as well. If you like white better than black, tell me as well. Thank you so much for watching. Till next time.